Hello everyone, Kodongwane the Native God here. Today I'll be taking you through question 2 of the Engineering Science in 3 exam that was written on the 31st of March 2023. Now question 2 is based on moments. So yeah, let's jump right into it. 2.1, give 2 types of loads acting on a beam. Right, so there are many types of loads we can get on a beam. You can get point loads, you can get uniformly distributed loads, you can get uniformly varying loads. Now, point loads and uniformly distributed loads are the ones that we are mostly familiar with for this level, right? But as you progress with moments, probably if you get to do strength of materials and structures, N5, you might deal with uniformly varying loads, right? So any 2 of the 3 that I've given you here would be the right answer, right? 2.2. Now 2.2 reads as follows: a beam is supported at its ends and is in equilibrium. It carries point loads of 5 kilonewtons, 5 meters, and 3.6 kilonewtons, 3 meters from the left end, and 6 kilonewtons, 4 meters from the right end. The length of the beam is 14 meters. The uniformly distributed load between the 6 kilonewton and 5 kilonewtons is 40 kgs per meter, right? Then 2.2.1, they say sketch a diagram and indicate all forces acting on the beam. So essentially what they're asking for is for us to draw a free body diagram of this loaded beam. Now, the free body diagram of this loaded beam will look like this. Right? Right, so they said we have a beam, right, which is supported at its ends. So at each end you find a support, right? So in this case I labeled the supports as blue, right? So each end of the beam has a support, right? And then they said it carries point loads of 5 kilonewtons, right? So 5 kilonewtons, 5 meters, and 3.6 kilonewtons, 3 meters from the left end, right? So from the left end, so from this end to 5 kilonewtons is 5 meters. Hence you see here 3 plus 2 is 5, right? And then 3.6 kilonewtons, 3 meters from the left end. So from the left end again to 3.6, it's 3 meters, right? And then we have 6 kilonewtons, right? 4 meters from the right. So 4 meters from this end, we have what? 6 kilonewtons, right? And then I said the length of the beam is 14 meters. And then the uniformly distributed load, so we have a UDL between 6 and 5 kilonewtons, right? So between 6 and 5 kilonewtons, right, we have a uniformly distributed load, otherwise known as a UDL, and it is 40 kgs per meters, right? Right. Now, whenever we've been given a UDL, right, we resolve that the UDL or the magnitude of the UDL into its weight, right? So they've given us 40 kgs per meter, and we have to resolve that into a magnitude that resembles the weight of the beam, right? Meaning the UDL has to be in newtons, right? So in order to do that, they've given us 40 kgs per meter. So to resolve that into the UDL's weight, we're going to have to multiply the mass by 9,8 and then also multiply that by what? By the span of the beam, right? So when you multiply the UDL with the span of the beam, then we get the weight, because the span of the beam cancels with this M here, right? So meaning you would have to say 40 kgs per meter times what? Times 9,8, right? And then times the span of the beam. The span of the beam is what? Is 5 meters. So 4 times 5 meters, right? Which gives us what? Now if you punch this in your calculators, you are going to get, now because the point loads, if you look at them, they are in kilonewtons, right? So it's going to be better for us to have our weight in kilonewtons as well. So in kilonewtons, we get 1,960 kilonewtons. See, this and that cancels, and you're only left with the newtons, right? Right, so what do we get? We got 1,960 kilonewtons. And remember, the weight of anything acts at its center. So the weight of the beam is going to act at half the span of the UDL, right? Remember, the span of the UDL is 5 kilonewtons. Hence, the weight of the UDL is going to act at what? At half of that span. So half of 5 meters is what? 2,5 meters. So 2,5 from the right end and 2,5 from the left end, right? Hence you see the weight here of the beam is what? I've labeled it as being at the center of the span of the what? Of the UDL. Right, so that is 2,2.1. Right, so now we move on to two comma 2. So 2,2.2, right? Now 2,2.2 reads as follows. They want us to calculate the reaction of the supports. Now, as far as moments, it's always best to calculate the reactions or the reactions at the supports of the beam using moments, right? As opposed to using moments for one and then having to use Newton's third law of motion for the other, right? Because you might make a mistake when calculating for the one support using moments. So to avoid making a mistake, or to avoid mistakes, rather calculate both supports or the reaction of both supports using moments, right? Now I always advise students to label the free body diagram, meaning from the left end, say you're gonna have A, right? So from the left end, wherever you see a point load, you are going to give it a label, right? So your point load at 3,6 kilonewtons. So there you're gonna have your B. Then here's your next point load. You're gonna name this as C. Remember, the weight is not a point load, right? We had to resolve that from the UDL, right? But initially we didn't have the weight, we had a UDL. So remember, whenever you label your beam, you label it from the left and give labels to the point loads which you were given in your statement, right? So because the weight you weren't given it, we had to calculate the weight. You don't label the weight. So the next point load is 6 kilonewtons. Hence, you're going to have point D there. And then, of course, the end of the beam, you have to label as well. Now, in this case, it so happens that at the end of the beam, you have a support as well. Right? Then now you can calculate the reactions at the supports. So our reactions are reactions A and our reactions are reaction A and reaction E, right? So we're going to take moments to calculate for each reaction. First, we're going to take moments about E. So we're first going to take moments about E so that we can get A. Then once we've calculated A, we're going to take moments about A to get the reaction at support E. Right? So first, we take moments about E. Right? And we say sum of clockwise moments is equal to sum of anti-clockwise moments, right? So now if you're taking moments about E, right? If you're taking moments about E, you have to check each support and each point load, what moment effect it would have if we're taking moments about E, right? So if you're taking moments about E, what moment effect or what turning effect does support A have, right, when taking moments about E, right? So if you're taking moments about E, support A would have a what? It would have a clockwise turning effect, right? So support A is going to be part of clockwise moments. Now, if you look at all the other point loads, including the weight of the beam, right? All the other point loads, including the weight of the beam, are going to have an anti-clockwise effect if we are taking moments about. They're going to have a anti-clockwise turning effect if we're taking moments about point E, right? 3,6 is going downward, and if we're taking moments about E, it's going to tend to go in that direction, which is anti-clockwise. The 5 kilonewton force, the same, will tend to go in that direction. The weight of the UDL will also tend to go in that direction. 6 kilonewtons is going downward, and we're taking moments about E. E is this side, so it'll have a turning effect towards E. Now, whenever you're taking moments, your point loads and support must have a turning effect towards the point where you are taking moments, right? So all the other point loads as well as the weight will have an anti-clockwise turning effect towards point E. Right, so our only clockwise moments would be on the right support. So RA multiplied by, so A times the perpendicular distance from A to where we are taking moments. So E is what? 14. So times 14 is equal to 3,6 times, what is the distance between 3,6 and support E? It is 11. So 11 plus the 5 kilonewtons times the distance, which is what? 9 meters, plus the weight. The weight of the UDL is 1,960 times, what is the distance from the weight of the UDL to support E? It's 6,5. So 6,5 plus the 6 kilonewtons, 6 times 4 meters. Okay, let's do this here. Right. So we could have some space this side, so times 4. So this becomes 14 RA is equal to, now if you punch all of this in on the right, we are going to get 121,34, right? And because we're looking for RA, we want to make RA the subject, so we divide by 14 both sides. RA is equal to 8,667 kilonewtons. Always remember to round off your numbers to 3 decimal places, right? So we have RA. So now we are going to take moments. Now we take moments about A. So if you take moments about A, right, the only unknown would be the reaction at support E, right? So now we take moments about A, so you can calculate and get the magnitude of the reaction at support B. I mean support A, support E, sorry. So sum of clockwise moments is equal to sum of anti-clockwise moments. Now again, when you're taking moments, you investigate as to the turning effect each force or each point load and each support is going to have about the point in which you are taking moments. So the point in which you are taking moments is A, right? So what turning effect does each point load and support have towards point A, right? The reaction at E is going to have this turning effect, which is what? Anti-clockwise. So the reaction at support E is going anti-clockwise, and then all the other forces, so all your other point loads, including the weight, are going to go clockwise. That's going clockwise. This one is going clockwise. The weight of the UDL is going clockwise. The 6 kilonewtons also having a turning effect or a clockwise turning effect, right? So our only anti-clockwise moment is what is the reaction at support E. Right, so clockwise moments, we have the 3,6 kilonewtons, right, times the perpendicular distance, which is 3 meters, plus the 5 kilonewtons times 5 meters, which is the perpendicular distance, and then the weight is 1,960 times the perpendicular distance, which is 7,5, plus the 6 kilonewtons. So 6 kilonewtons times the perpendicular distance, which is what? 10. Right. Which is equal to the reaction at support E times the perpendicular distance, which is what? 14 meters. Now we're looking for RE, so we're going to make RE the subject. 14 RE is equal to what? Now if you punch what's on the left of this algebraic expression, we are going to get 110.5. Right, so because we're looking for RE, we're going to divide each side by 14. So that goes, and if you punch this in your calculators, we are going to get 7,893 kilonewtons. Right, so we have taken moments to calculate the magnitudes of both the reactions at the supports. So now we use Newton's third law of motion to see if our beam really is in equilibrium, right? If it is in equilibrium, then forces going up must be equal to forces going down. So let's prove that. Sum of forces going up is equal to sum of forces going down, right? Forces going up is what? Is reaction A and reaction E. So reaction A is 8,667 plus reaction E, which is 7,893, is equal to all the forces going down is 3,6 plus 5 plus the weight of the beam, which is 1,960 plus what? The 6 kilonewtons, right? So this should give us the forces on the left must be equal to the forces on the right. So if you punch this in your calculators, let's see what we get. 7,893. So this side we get 16,56 kilonewtons. We should get the same thing this side. So 3,6 plus 5 plus 1,96 plus 6. So we are getting the same thing, 16,56 kilonewtons. Now, forces going up and forces going down are equal. So this means that based on the calculations we've made, there's a good chance that our reactions at the supports are correct. Now the reason why I say that is because you might have made a mistake, but because you calculated your mistake in a right way, you find that as far as the numbers balance, right? So hopefully we haven't made a mistake here, right? So let's move on to question 2.2.3. Right, so 2.2.2 was 4 marks. So if you do this, right, you should get 4 marks. Right, it's always important, even though maybe they haven't mentioned it in the question, to prove your answers, right? To try and make sure that at least based on your calculations, at least the beam is in equilibrium, right? So now we do 2.2.3. Right, so 2.2.3, they want us to draw a shear force diagram, right, of this beam. Right, they want us to draw the shear force diagram of this beam. So what we are going to do is we're going to take the free body diagram and we're going to copy this. Right, so we are going to draw our shear force diagram from our free body diagram of our beam, right? We don't need this anymore. Yeah, we don't need that, right? But we do need for our UDL to be in what? In newtons per meter. Remember, we multiplied the 40 kgs by what? By 9,8. So this here is 392 newtons. 392 newtons per meter, right? And we leave our UDL in that form, right? So now we need to draw our shear force diagram, right? To draw our shear force diagram, we need to have, we need to show our sections. Now, as far as sections, we section the beam on the, I always tell students to section the beam on the right hand side of each point. Now we have how many points here? A, B, C, D, E, right? 1, 2, 3, 4, 5. We have 5 points, right? So we're gonna section the beam on the right hand side of each point, right? Now, on points where we have to take into consideration the UDL, at those points we are going to section the beam on either side of the point. Meaning what? Meaning you don't just section on the right hand side of the point, but you section on the left hand side of the point as well, right? I'll show you what I mean by that just now. So if you get to each point and there's no beam on the left of that point, right? So you're just going to section on the right hand side of the point, right? But if you get to a point and on the left of that point there's a UDL, then you're going to section on the right hand side as well as on the left hand side of that point. Meaning, for instance, point A, right? Point A, on the left of A, there's, well, obviously nothing, right? So you're just going to section, right? You're just going to section on the right hand side of point A, right? And then you get to point B. When you get to point B, on the left of point B there is no UDL, so you only section on the right of what? Of point B. You get to point C, on the left of point C there's no UDL, so you only section on the right of point C, right? Then you get to point D. At point D, you look at the left of point D, we have a UDL on the left of point D. Therefore, because we have a UDL on the left hand side of point D, we are going to section on the right of point D as well as on the left of point D. So we section on either side of point D, right? Then we get to point E, right? At point E, on the left of point E, there's no UDL, right? At the left of point, at the left side of point E, there's no UDL, right? So at that point, you're in a section on the right of this point, right? And then we draw our shear force diagram considering the sections we have labeled, or the sections we have, the sections we've drawn on our free body diagram, right? Right. Let's draw our shear force diagram. Now, as far as the scale of your shear force diagram, you use any suitable scale, right? You use any suitable scale. Now, as far as going into much detail, I think as you can see, I'm trying my best not to go into much details because this is an exam. But if you're interested in knowing how to go about doing problems based on moments, you can follow the channel, hit that notification button, right, so that you don't miss any of the lessons I'm going to post based on engineering science. And there are other subjects I'm going to be posting content of, hence me saying if you're doing any of the mechanical engineering net subjects, hit that notification and subscribe button so that you don't miss any of the content I post based on such subjects. So you're gonna have 0 newtons here. Zero kilonewtons. So 0 kilonewtons. Right. So let's start drawing our shear force diagram. Right. So we first consider the section at A. There's only one section at A, which is on the right hand side of A. Right. So we are going to consider forces on the left of this section. Right. So we're going to consider forces on the left of this section. Now, forces on the left of this section is what? Is the reaction support at A. The reaction support at A is what? It is 8,667 kilonewtons, right? And the reaction support at E was 7,893 kilonewtons, right? So again, we consider the section at A, and at A we only have the reaction support at A. Forces going up, therefore we take it as positive. Remember, forces going up, we take them as positive, and forces going down, we take them as negative. So we're going to have force going up is what? Is 8,667. So you're gonna have 8,667 right, and I have 8,667 kilonewtons, right? That's the only force at section A. So now we move on to section B. So because between section A and section B there is no UDL, right? You draw a straight line going across, right? Because there's no UDL between section A and B, you draw a straight line going across, right? Then when you get to B, the only force that gets introduced now is the 3.6 kilonewton force, which is going down, right? Remember, before getting to B, we had established that the only force that exists is what? 8,667. So now we are at point B, and the only other force that gets introduced is what? Is 3.6 kilonewtons. It is negative because it is headed downwards. So what do we say? We say 8,667 kilonewtons minus 3.6 kilonewtons, right? And if you punch that in your calculators, we get 5,067 kilonewtons, right? So 5, let's say it's going to be a force that's run about there, right? So this is 5,067 kilonewtons, right? Then we are done with section B. So we go to section C. Because there's no UDL between B and C, we draw a line going straight across, right? When we get to C, remember, before we get to C, we are at 5,067 kilonewtons, right? So whatever force that gets introduced when we get to section C is either going to be added to or subtracted from what? 5,067. So when you get to point C or section C, the only other force that gets introduced is what? Is 5 kilonewtons. It's going downwards, so it is negative. Hence, we are going to subtract the 5 kilonewtons from the what? From the 5,067 kilonewtons. So if you subtract that, what do we get? Right, we are going to get 0,067. So we get 0,067 kilonewtons, right? We get 0, maybe this is not clear. We get 0,067 kilonewtons, right? That's forces up to section C. So now we go to section D. Now section D has sections on either side of section D, right? So first we're gonna deal with the section on the left, and then we're gonna deal with the section on the right of D, right? Now, because there's a UDL between C and D, right, the line we're going to draw going across is going to what? Or the line we're going to draw going from C to D is going to be a diagonal one, because we have a UDL. So whenever you draw a line between points where there's a UDL, the line has to be diagonal, right? Now, if you get to section D, first the left section, right? First the left section, right? So the only force we get is based on the UDL, right? Now the UDL is what? Is 392 newtons per meter, right? So what do? You take that and you multiply it by what? By the span of the beam, right? So we say 392. So you're going to say 392 times the span of the beam. The span of the beam is what? Is 5 meters, right? So 392 newtons times what? The span of the beam, which is 5 meters. And what do we get? We get 1,960 kilonewtons, right? Now, because once you've resolved the UDL into its weight, the weight is acting downward, right, we are going to say, or we are going to subtract the what? The weight of the UDL in this span, right, from what? From the 0,067, right? So we are going to say 0,067 minus the 1,96, right? And what do you get? We get minus 1,893, right? We get minus 1,893 kilonewtons. 893 kilonewtons, right? Let's say it's this point, right? So again, because there's a UDL between C and D, right, the line you're going to draw between them is going to be a diagonal one, meaning from section C to section D, we are going to have a diagonal line, right, representing the UDL between the what? Between section C and section D, right? So when we say 0,067 kilonewtons minus essentially the weight of the beam, which is 1,96, right, we get minus 1,983 kilonewtons, right? That is the section, that is the left section at point D. Now we deal with the section on the right, right? Section on the right, the only force that gets introduced now is what? Is the 6 kilonewtons. Remember, when we're dealing with the section on the left, right, because the 6 kilonewtons was on the right hand side of this section, and we only consider forces on what? On the left of this section. We didn't include this force, right? But now we are looking at the section on the right of D, right? And when you get to that section, only then do we consider the 6 kilonewtons. Why? The 6 kilonewtons is now on the left hand side of this section, and we only consider forces on the left hand side, right, of each section, right? Now remember, we are already at what? At minus 1,893 kilonewtons. So we take the minus 1,893 kilonewtons and we subtract the 6 kilonewtons, right? So when we do that, remember, we are still at point D, right? So whatever answer you get, if it's positive, then you would go up, right? If the answer you get is negative, then you draw a line going straight down, because remember, both sections are at point D, right? So minus 1,893 kilonewtons minus 6 kilonewtons. Remember, the 6 kilonewtons is going downward, so it is negative. And what do we get? We get minus 7,893 kilonewtons. So we draw a line going downward, right? And then we're done with sections D, right? We've considered both sections, so now we move on to section E, right? Now, between point D and point E, there is no UDL, right? Therefore, we'll draw a line going straight across from section C, or from section D, or from point D, right? And then when we get to section E, we consider forces on the left of section E, and the only force between D and E is what? is the reaction support at what? At point E, right? The reaction support is going up, hence we take it as positive. So what do? We are going to add the 7,893 kilonewtons to the minus 7,893 kilonewtons. And what do we get? We obviously get 0, right? Now, your shear force diagram starts at 0, and because your beam is statically determinate or is in equilibrium, it must always go back to 0, right? So it started at 0, and because our beam is in equilibrium, it has to end at 0, which this one does. Right? And there we go. This is your shear force diagram. Right, so the orange part of this diagram is your shear force diagram. Right? This is 4 marks. And yeah, this will be your 4 marks. Right? Now, because I know a lot of students struggle with shear force diagrams, so if you find yourself struggling with shear force diagrams or moments in general, just hit that notification button, subscribe to the channel, and hit that notification button so that you don't miss any videos I post, because I did mention on our first video that I'm going to be posting lessons based on engineering science modules, right? So if you feel like my content is to your liking, then please hit that subscribe button, and then hit the notification button as well, so that you don't miss any content I post, right? I'll also be posting content based on engineering science N4, and I'll also be posting mechanotechnics N4, and then eventually I'll be doing content based on all the other subjects. So your strength of materials N5 and 6, mechanotechnics N5 and 6, etc. Right? If you're in mechanical engineering, if you're in mechanical engineering department, then you and I will be buddies for the next years to come, right? I really hope you found this helpful, and if you did, again, subscribe to the channel and hit that notification button. Yeah, good luck to everyone. Thanks.